Hello, welcome back. Today we're going to be covering how to conduct a chi-square analysis in Jamovi. In this video specifically, we're going to be covering two different types of chi-square analysis. So first, we're going to cover the chi-square goodness of fit test, and then we're going to cover the chi-square test of independence. So by the end of this video, my goal for you is that you're going to know what these types of analyses are, when you would use them, some example research questions, and then I'm also going to cover how to conduct these analyses in Jamovi, including how to make sure that you have met the assumptions of the analyses. So I've got the data set linked in the description below. I encourage you to open it up, follow along on your own device, and let's get into it. So to begin, let's talk about what a chi-square analysis is. So we mentioned briefly in previous videos that sometimes in certain situations, we might need to use what's called a non-parametric test. And this type of test has different, typically much less stringent assumptions than a typical parametric test. Parametric test being all the other things we've covered so far. So t-tests, ANOVA, regressions, those are all parametric tests that have an important set of assumptions. There are also assumptions associated with the chi-square types of tests, but as I mentioned, these assumptions are going to be slightly different and less stringent. So to begin, we usually talk about the importance of normality, that our dependent variable needs to be normally distributed. This is not one of the assumptions of the chi-square test, meaning that if you have data that are not perfectly normal, a non-parametric test is going to be much more okay with deviations from normal. One of the assumptions that will stick around is the assumption of independence. So it's still important for our data to be independent from one another in the chi-square test. However, we also don't have assumptions for things like homogeneity of variance, heteroscedasticity, things like that we've covered in previous videos are not part of the set of assumptions for the chi-square test. So what specifically are the set of assumptions for chi-square? Well, as I mentioned, we do still have the assumption of independence. We also have the assumption that the categories for the chi-square test, because in this case, we're going to be using categorical data instead of continuous data, that those categories be mutually exclusive and exhaustive. And then finally, we have the requirement or the assumption that there are at least 5 frequencies in each of the categories. So all of these assumptions, independence, mutually exclusive and exhaustive categories, and needing a minimum of 5 frequencies in each category, these are actually all things that we would assess prior to conducting the analysis. So we would want to take care of all of these pieces when we are doing research design and data collection. We actually don't test any of these assumptions within Jamovi itself. So when we open up Jamovi here in a little bit, we are going to be able to breeze past some of those assumptions checking and get right into the analysis. The specific research question that we're going to be working with today, first for the chi-square goodness of fit test, is let's say that we want to know if there is a difference in the expected versus observed frequency of speeding tickets for different kinds of vehicles. So in an ideal world, of course, having a certain kind of vehicle wouldn't mean that you get a different amount of speeding tickets, right? However, we're just going to do a little experiment here and see if there is a difference. And of course, I mean that term experiment, not literally. We're just going to be running an analysis here. So we've got 3 different types of vehicles we're going to compare. We're going to take a look at 4-door sedans. We're going to take a look at SUVs, and we're going to take a look at trucks. And we would expect that the frequency of speeding tickets would be the same for all 3 different types. So that kind of question, we've got a categorical variable. We have just, categories of car. And then we also are not comparing means the way we might in a parametric type of test. Instead, with a non-parametric chi-square test, we get to compare things besides means. In this case, we get to compare frequencies. So this is the perfect research question to walk us through what it will be like to conduct a chi-square goodness of fit test in Jamovi. All right, so moving on from the assumptions, we are going to use a goodness of fit test. That means that we are looking at the frequencies across different categories of just one variable. That's a situation where we would use this type of chi-square. Let's go ahead and open up Jamovi and take a look at the data here. So you're going to go to analyses, and then you're going to go to frequencies, and you're going to select the goodness of fit test, and it's going to be labeled in outcomes, and then you're going to see the little chi-square symbol and it says goodness of fit. So that's what you're going to select. And then you're going to move over vehicle type into the variable box there. And I'm going to also have you clicked on expected counts. Now, you'll see here we have our categories. So we have a sedan, an SUV, and a truck. Actually, I might have misspoke earlier and said motorcycle. We're looking at a sedan, an SUV, and a truck. So in the ratio section there, we are going to keep these all as a 1-to-1-to-1 ratio, right? Because what we are predicting is that the frequencies should be the same for all three of these cars. And then we're going to compare that to what actually ends up happening. So the buttons that you click here in terms of ratio might differ depending on your specific prediction. Here, we are predicting that they would all be the same. So the ratios are 1-1-1, and you can see that that is reflected as well in the proportions. So once you click on expected counts and expected proportions and have your ratios set, you'll see the data over in the output section. And we have a couple of things that I want to bring your attention to. So we have each level, the sedan, the SUV, and the truck. And then we have the observed and expected frequency. So we had 150 different cars, 50 in each category, right? Because we expected for the frequencies to be even. So each of the expected counts is going to read 50, but then we have the actual observed counts, or what really happened in terms of speeding tickets. And that's where we're going to see differences between what was expected and what was observed. Now, to determine if those differences are just chance differences or if those differences are actually statistically significant, that's where I'm going to turn your attention to the chi-square results. So we have the chi-square statistic, which is 13 here. We have degrees of freedom, and then we also have the p-value. So we will know that this is statistically significant if our p-value is less than 0.05. And here we have a p-value of 0.002. So what this tells us is that the differences in the observed frequencies and the expected frequencies across these three different vehicle types is statistically significant. And if you take a look at the specific values here, so we've got 55 is the observed frequency for the sedans, 30 is the observed frequency for the SUVs, and 65 is the observed frequency for trucks. So trucks are getting the most speeding tickets with 15 more than what would be expected. And then we also see that SUVs are getting quite a bit less speeding tickets with only 30 compared to the 50 that would be expected. So this helps give us a little bit more insight into where the statistically significant difference is coming from there. So it really is as simple as that. A chi-square, compared to other kinds of analysis that we've covered, is a fairly simple one. So if you have any questions at all about chi-square and goodness of fit test specifically, please leave them below. I'm happy to answer or work with you. And actually, we're going to move on now in this same video to another type of chi-square analysis called the chi-square test of independence. So the next type of chi-square that we're going to be covering is called the chi-square test of independence. And unlike with the goodness of fit test, where we only have one categorical variable, in the test of independence, we are working with two categorical variables, and we can use this test to examine whether being a member of one category is independent of the other. So the example that we're going to be using today is looking at if being in a category of grade level, so middle or high school, is independent from reported levels of alcohol use. So oftentimes at schools, students will be given these large surveys that will try and assess their engagement in different risky behaviors. So it might ask students if they have participated in underage drinking, for example. So we're going to take a look at if the likelihood of reporting that you have participated in that underage drinking or alcohol use is independent from the grade level that you are in, being a middle schooler or a high schooler. So in Jamovi, if you open up the data set, we are going to go to analyses, and we're going to again click on frequencies, but instead of selecting the goodness of fit test, this time we're going to be selecting the independent samples test, or Jamovi also labels it as the chi-square test of association. Test of association, test of independence, those are interchangeable. So you're going to select that option. And then you are going to have rows and columns, and you're going to move over the alcohol use into the rows and then the grade level into the columns. It really doesn't matter the order that you do these in, by the way, you'll get the same results. So after you have selected that, you're going to click on statistics, and you're going to see that this gives us a lot more options than we had in the goodness of fit test. So you'll see that chi-square is selected. That's wonderful. You can also have the confidence intervals selected. Under the hypotheses tab, you'll see that we can make clear that our hypotheses is that the groups will not be equal to one another. What I want to draw your attention to specifically is the option to select something called Phi and Cramer's V. This is going to be our measure of effect size here, and so I am going to have you select that. Then if you scroll down to cells, you'll see that you can ask for the observed and the expected count, so you can select that. And then if you'd like to, you can also add in percentages for both the row, the column, or the total, and I can leave it up to you whether you'd like to ask for that data or not. Okay, so if we take a look at the contingency tables here, we're going to see a couple of important pieces of information. So you're going to see the categories that we have here. So we have alcohol use broken down into yes or no, and then we have grade level broken down into middle and high school. Then finally, we have both our observed frequencies, so what actually was reported, and what we would have expected. So we might have expected for high schoolers to report a little bit more use of alcohol compared to middle schoolers. And we can see that that did hold up, but at a different frequency than what we would have expected. So we expected for the counts to be around 50 for high school and around 40 for middle school. And what actually happened was it was around 62 for the high schoolers and 29 for the middle schoolers. Then if we take a look at the no category for alcohol use, we expected to see around 27 middle schoolers report no and around 32 high schoolers report no. But what we actually found was that 40 middle schoolers reported no and 20 high schoolers reported no. So we can take a look and see, yes, there is a difference in the observed versus the expected frequencies for the alcohol use and the grade level. However, what the p-value here is going to tell us is if that difference is actually statistically significant. And it looks like here we can confirm that it indeed is, because our p-value is less than 0.001, so that's less than that 0.05 threshold. So we can say, yes, there is a dependence between grade level and reported use of alcohol and a difference in those expected and observed frequencies. Now, remember earlier I had asked you to select for something called Cramer's V. That's going to be our effect size here for this test of independence. This effect size can be interpreted similarly to a correlation. So with correlations, our typical rule of thumb would be that correlation around 0.2 or 0.3 would be a small correlation, around 0.5 would be moderate, and around 7 or 8 would start to be considered a large or a strong correlation. So here our Cramer's V value is 0.336. So we would probably say that that is a small to maybe very lightly moderate correlation between alcohol use and grade level. So to wrap up here, we've covered two types of chi-square analysis. We've covered the goodness of fit test for if you have one categorical variable and you're comparing frequencies. Then we also covered the test of independence for if you have two categorical variables and you are comparing frequencies to test and see if being a member of one group is independent of being a member of another group. If you have any questions about these types of analyses, please feel free to leave your questions down below and I'm happy to get back to you, or I can work with you more independently on joytoteach.com. Thank you so much.